And here we go. We have liftoff. Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, roll, planet.
Water towers fly! Yes!
Echo down to nominal.
Flight downside FD off. Bring in FD off. Off. It's orange!
125. Oh my God! Oh my God!
Decollage.
Look at this!
Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
The methane would be igniting the flare, correct?
Yikes. You dead? Sure. We don't need any more of these.
All right, folks, it is Sunday, about the end of the month coming up here, so you know what time it is. It's time for another Intrepid Museum Astro Live, where we do some STEM outreach. We talk to scientists, we talk to engineers who are doing cool missions. We've got live Q&A. We're not all pre-recorded or anything here, so we will be hopping right into the show today. Now, remember, we do these on a monthly basis, but we took a little bit of a hiatus there for a little bit of time. Should have some shows coming up through the rest of the year, but this is Intrepid Museum's Astro Live, the STEM outreach shows we've been doing for, I don't even know how many years now, like 5, 6, 7, 8 years now. We have been helping Intrepid spread their good work and the work of the scientists and engineers that make cool missions in space and beyond. I don't really know what's beyond space, but we'll figure it out. Today we're going to be talking about space weather and how we measure some of the things that are going on in the upper atmosphere and how that affects, or probably more accurately is affected by the solar winds and auroras getting formed and all that sort of stuff. So my name is John Galloway. I'm with NSF. With me today, we'll have some scientists, but we'll also have Alicia Siegel. I think we've got Alicia on here, right? There she is. How you doing, Alicia?
Oh, great. You know, you're right. It has actually been, I think, about 6 months since we've done one of these. Obviously, we've done some on-sites, but
virtual ones, yeah.
Virtual ones, it's been a while. So yay. Hello. Welcome, everyone.
Surprise, we're back.
We are back. And actually, it's really exciting topic this month. So if you tuned in back in April for our on-site astronomy night, you might have known that we had some people from the Parker Solar Probe who work, of course, in conjunction with the Johns Hopkins Applied Physics Lab. It was a really, really great event. They were so kind. They stayed for so long and, you know, answered everyone's amazing questions, of course. But then afterwards, we were like, what else can we do to help promote some of this cool heliophysics that you guys are doing there? And so we actually were also connected now with the EZIE team. EZIE is NASA's Electrojet Zeeman Imaging Explorer.
There was a whole thing there. I was going to ask how we're supposed to pronounce that. Like, if you look at the stream title, it's EZIE, but is it like EZE or EZIE or just EZIE?
Well,
do you say all the letters EZIE?
I've been assuming it's easy.
We'll ask the scientist. We'll have the scientists tell us how to pronounce their mission.
Yeah. But this mission is really cool. It's the first to study electric currents in Earth's upper atmosphere, known as these auroral electrojets. So, you know, we see the auroras. It's been a very busy heliophysics, you know, past year or so. Even up here in New York, we've been able to see some auroras in our sky, which is bizarre because the light pollution alone is terrible. But it's these powerful ribbons of energy that drive the northern and southern lights. So this mission has this trio of CubeSats that study them. And we've got a scientist and we've got an engineer from the team who are here to talk to us today.
Alicia, time out. I thought we were interviewing a band. The like auroral electrojets is a cool band name, honestly.
I played bass for them in college.
You played bass for them in college, nice. The auroral electrojets. So, folks, you know how this goes. We appreciate y'all showing up, but the shows don't just sort of roll themselves, right? Alicia, we're still operating under the NASA grant, aren't we here?
Yeah. Yes, thank you to our grant providers, of course. Astro Live is supported through a NASA cooperative agreement to the New York Space Grant Consortium.
There you go.
So
thank you
for their support as well. And let's bring on our guest, shall we?
Let's hop right in. Let's hop in and get the guests over on the show and start talking auroral electrojets. Say that 10 times fast.
So with us today, from left to right here, we've got Dr. Jesper Gello, who is the project scientist for NASA's EZIE mission at the Johns Hopkins Applied Physics Laboratory, and also a worldwide leading expert in the area of magnetosphere-ionosphere interactions, with a particular focus on the vast electrical circuit that links Earth and the surrounding space. He can tell you a lot more about what that means in just a bit. And then we also have Rob Barnes, who's the ground systems engineer for the NASA EZIE mission. He was born and educated in the UK and came to work at the Applied Physics Lab in '97 as a software engineer. He was working on the ionospheric radar in the Arctic and Antarctic, and he worked with Jesper on developing the SuperMag facility for ground magnometers. Am I saying that right?
Magnometers?
Magnetometers.
Magnetometer. There's an extra magnet in there. Magnetometers.
And he also became the ground systems engineer for the EZIE mission in 2020. He's going to actually, in a bit, talk a little bit about a really cool kind of outreach thing that they've developed for this as well, which we're excited to share with you too. But welcome, everyone. Enough of us blabbering on. Welcome to the show.
Well, let's get the first question real quick. Is it easy? Do we just say easy? Are we saying it right? Or are you like rolling your eyes like, oh gosh, they don't even know how to say the mission name? Like, it's just NASA's EZIE mission.
So first and foremost, I feel like we should make that band, right? Now I agree. That sounds pretty cool. I mean, I'm sure my kids would feel I'm cooler than so.
if you were the lead singer of the auroral electrojets, that's awesome.
I can't sing, but my daughter can. So, but anyway,
It be a middle-aged dad band, yes. But
so anyway, joking aside, actually, I don't like acronyms for missions. I think they're always so attempted. But in this particular case, it rolls off your tongue, right? It's the EZIE mission, and it is anything but easy.
I'm about to say,
it is
not an easy mission to do.
It's incredibly complicated. Both the physics, the engineering, the data processing, you name it. But we call it the EZIE mission, so you cannot imagine how many jokes there's been about that, right? So.
I'm sure we'll get some on the show today, but so tell us a little bit about the mission. Like, have we already launched the mission? Is it on its way to space? Is it in a warehouse somewhere waiting to launch? What's your current status for your satellites?
So it launched on March 15, 3 small spacecraft, and they launched from Vandenberg on a SpaceX launch, and they've been up ever since. We deployed and now in orbit around the Earth in a polar orbit. It's what's called a sun-synchronous orbit. It takes them 90 minutes every orbit, but they always look towards the same local time. Here's the launch, actually, which is, you can't help it, but SpaceX does cool things, right? So here you see it. And keep in mind, everybody, at this point in time, we sit there and we are shaking and nervous because we've spent years developing these spacecraft, and they're there in the nose cone, and we're hoping for the best, right? So, you're kind of nervous about it. So,
with SpaceX, you got pretty good chances with SpaceX. Riding on a Falcon 9. Falcon 9 has been putting an awful lot of satellites in orbit. Just the satellites, like
it's
3
still
satellites.
Your little babies. It's still your little babies up there, and you like.
Jesper, were you at the launch itself?
No, the thing is that we had all launch parties, and NASA had everything sent up with the media and what have you, and it all got delayed. The launch got delayed and delayed and delayed, and at the end, the NASA team essentially had to go home, return home, because they'd been there for like a month. They were there also for the Punch launch, the Punch mission, and we were right after, and everything just got delayed so many times that unfortunately we only saw it on and
we
live.
saw it in the conference room at APL at, I think it was 1:30 in the morning.
Wow.
And the one interesting thing is this launch, this Falcon 9 launch, it was what they call a transporter, and we were part of one of 65 payloads that were deployed that day.
65 payloads.
5 payloads.
Were you 3 of 65 payloads, or were your 3 satellites? You were 3 of 65. Okay, because you had 3 smaller satellites. These transporter missions or rideshare missions are almost like a clown car, where there's a bunch of smaller satellites, and they start deploying, and it takes them forever to deploy because there's so many satellites.
You can see it here. If you look to the left of the picture here, right behind Rob and you, Jack, the first one will get deployed. I don't know how far we are in the movie, but you see them come out here. Is it playing? Maybe we missed it.
It's playing.
Yeah, it's moving.
There goes the second. That's the second.
That's EZIE.
There's another one. of hours, and if we wait a little bit, we'll see the last one. But essentially, there you're literally live seeing your little friends go out, off to college, and you're hoping for the best, right? So please be kind. But luckily, ever since, they've actually been calling home. So these are little CubeSats. They're not bigger than like a little carry-on, essentially.
Right.
They're incredibly capable, and we essentially got funded by NASA because it was so innovative, this mission. What we are doing is we have one instrument on each of these spacecraft. It's the same, they're identical. That gives redundancy, but it also allows us to see how things are evolving and so on. So, the last one went off there, but we also have movies about that, by the way. But yeah, they went off, but ever since that, they've been well behaved. The commissioning of the spacecraft went really well. We have no problem. The instrument itself is incredible. JPL built that instrument and have done a fantastic job. And we are getting data down now. We are now in what's called phase E, where we are essentially doing the science operation. Right. Everything is checked off. Everything is behaving. All three spacecraft, instrument, everything is moving very, very nicely. It's a very small mission, keep in mind. The budget is $65 million, I think, in total.
Right.
And it's called a mission of opportunity. So it's a small budget, but it gives you a chance to try something new. And we were funded to do that under NASA heliophysics. It's linked to essentially space weather, as you started out by saying.
Yep.
Because it is the conditions that we live in here, right, in our world, our home here on Earth. So heliophysics is, again, the study of how the sun, the solar system, they all interact and how it evolves. So it's a study of the planets and the sun and everything in between there. So
okay, let's talk a little bit about that. They're small satellites. There were 65 payloads on that SpaceX launch, and you were 3 of the payloads, right? You have one sensor on each satellite. What enabled you to fit the science, I guess, the sensor that you need on such a small satellite? Is it new technology that was developed that lets you fit it in a small package, some breakthrough or something, or is it just, oh yeah, this is always fit in the small package? Like how can you fit your science in such a small satellite?
So the prototype for this instrument was actually flown on the space station, and it was the size of a couple of washing machines. It's quite a big payload. And it's just that the technology has advanced and miniaturization has advanced so much that we were able to squeeze it down to get it to this very, very small, what they call 6U size form factor.
Right.
And it's things like we need very precise timing to take some of these measurements. So we have this thing called the chip scale atomic clock, which is literally an atomic clock in a chip scale format.
Like a single chip, like you don't have to have a huge thing. It's just one little chip on the board is the atomic clock.
Yep.
No kidding.
And yeah, it's just a miracle of miniaturization.
Okay. So because of that, you were able to shrink it down, and you didn't need to be a refrigerator, a school bus, or anything like that. You know, these old satellites you think of are these big, massive things. But now we can get these sensors in much smaller satellites. And yours was 6U, you said? Or was that the total? It's 6U per satellite?
Yes, 6U per satellite.
Okay, so that's like 1U is you could sort of hold it in your hand, and 6U is just 6 of those, but you could still
literally the size, a little bigger than a bread bin or a little bigger than a shoebox. So there you go. You can see it on the bench.
It would fit in the carry-on overhead space of your airline?
Yep.
Actually, the picture there you're looking at is actually with the dispenser. So the satellite is inside.
Right, yeah, the satellites are inside those.
Oh, no kidding.
Even smaller than that. Of course, the solar panels fold out and all that, right?
Yep. There's like a tool case or something in the background there, I think a little bit off in the distance. But these are like carry-on sized satellites that you can fit the sensors into. Did you ever have to transport them that way? Did you like get on and they give you a little green tag and they gate checked it, and then you're like, no, this is a satellite. You can't put it under the plane. I have to take it on.
That has happened on a previous mission that I was on.
Really?
Yeah. So
on a plane?
On Valon probes, one instrument, I can't remember which one it was, they actually did have to buy a plane ticket, and they put in a box, and they got all the permission forms, and they hand carried it and flew it. I think it was from Iowa, and they flew it from Iowa down to the Cape.
No kidding.
Yeah.
I was just kidding about the size of the satellite, and apparently that's actually a thing transporting
it. Has happened in the past.
No kidding.
These were actually transported across from the spacecraft manufacturer, Blue Canyon, to Vandenberg, and we had them on a truck, and we got updates all the time to see where the truck was.
Right.
So to ensure that everything is progressing the way it's supposed to. So
I have to ask, like, we're so used to these big huge satellites. I know CubeSats aren't new. Were there other things on the truck? It wasn't like a FedEx truck and there was like somebody's Amazon orders and stuff like that. And your satellites are there too. Was this a specialized truck, or the truck was just transporting your satellites, or were they like mixed in with other cargo that needed to go to Vandenberg?
I think it was a JPL truck, so I think it was just our satellites.
Okay.
yeah,
So it's not quite at the point where we trust FedEx to transport, $10 million instrument.
We're not to that level of a budget or mass scale production of these sorts of things yet, are we?
No.
Okay.
I have a question. You said there were three of them in particular. Why are there three? And how do they work together? What is the whole point of having three of them like that as opposed to just one thing?
yeah, so we have a movie about how the EZIE spacecraft actually flying over the aurora.
Yeah.
And each of the instrument, the payload consists of essentially 4 beams that look direction down toward Earth. So each of them make a measurement of what happens in the ionosphere at 4 different foot points. Now, as they move across, and you see they make measurement as they're moving across in like a push broom configuration. And that means that the first spacecraft, we can make a map, essentially a map of what the electric current looks like. So that's great. We can see how it's structured. Now, the next one comes by 2 minutes or 5 minutes or 10 minutes later, and it does the same. And that allows us now to see how did it change this pattern. The third one comes by. So they each provide a snapshot of what it looks like, but between them, we can see how it's evolving too. So that gives us 2 things that allows us to finally address some of the fundamental science that we have basically been discussing for 50 years, which is how is the electrojet structured, this very intense current in the ionosphere. Yeah, here's the illustration.
There you go.
The first one coming by, they're basically looking down each of these beams, and it makes a map of the electrical current that's flowing in the ionosphere, upper atmosphere. And then we can make those inversions and do that. And again, then we can see how it's evolving. Again, that allows us to basically resolve a debate that's been for 50 years, hotly debated topic of how these currents are organized. At the end of the day, it is how Earth is really coupled to the surrounding space.
Right.
The key parameter is these electrical currents. Imagine like a massive electrical circuit flowing between Earth and the surrounding space. That's essentially what it is. But we still, believe it or not, don't know how that currents flow. We're still confused.
So it's almost like by having 3 satellites that sort of pass in, I'll say rapid succession, instead of waiting for one satellite to do an entire orbit and you get one reading every 90 minutes or whatever, right? If you have 3 sort of flying in formation and you have one and then a couple minutes one and a couple minutes one, you almost get more temporal resolution, like time resolution over the changes in the electrical currents, right?
That's right. So the interesting thing is that one of the things with EZIE is we don't have any propellant. We don't have any engines on board, no retros or anything. So the way we actually coordinate the observations, actually move the spacecraft, is we actually tip, there's enough residual atmosphere at that height, about 590 kilometers where we're actually orbiting, that we can actually use the atmosphere as a drag. So we flip the spacecraft up so the solar panels face into the direction we're flying.
Right.
The drag on those panels will actually then drop us in the atmosphere, and then we can rearrange the spacing between the satellites.
Okay.
That was actually one of the new engineering things that we did with the EZIE mission.
It's almost like an air brake. You just turn the solar panels instead of flat where they have less drag, and it's really thin atmosphere, but there's enough to make a difference. Instead of having the thin solar panel, just the air go around it like this, you turn them like that, and that gets you more drag, and they sort of function as an air brake, and you adjust your orbit not by using fuel, but just by sticking your hand out the car window. Everybody knows what I'm talking about, right? You stick your hand out the car window, and you can feel the air pushing on it. Same sort of thing, roughly, right?
That's exactly it. And we actually...
Exactly that.
Yeah.
Okay. No kidding. And so you can only do that a certain number of times. The satellites can't reboost themselves, right? But you can adjust their phasing just by slowing down a little bit, slowing down a little bit.
So we were in this weird position where we wanted to launch at a very solar active time. But the problem with that, when you get lots of solar activity, the atmosphere actually thickens and gets denser. And so we were kind of having this trade-off of, well, if we launch now, we can have a longer mission. If we wait, then we're going to have a thicker atmosphere. We'll have a shorter mission. So currently, we're actually, we have a 15, 16-month mission. And then after that, we will come back down. We'll deorbit.
Gotcha. So, folks, as we go through here, remember, we are going to take some questions. If you have questions for us, tag us in chat. There's a few different chats that you could find us in. But to whichever channel you're on, if you're on the NASA Spaceflight channel, tag at NASA Spaceflight. You're on the Intrepid channel, tag at Intrepid. Just wherever you are, tag it, and I'll see if I can't get some of these questions. But I've seen a couple of things about what exactly are you measuring? It's not like you've got a little voltmeter and you're sticking it into the aurora or anything like that. How do you measure the electric field of something without touching it?
So that's a fantastic question, actually, and it's really fascinating. Largely why we want this mission in the first place, because historically you have a magnetometer, which is an instrument that measures the magnetic field, a little bit like a compass you hold in your hand.
Right.
It measures the magnetic field right here. That's what you fly, and then you're stuck at whatever altitude your spacecraft is. This is different. As you saw in the movie, we have 4 beams that look down. They basically look at emissions coming up from a layer of oxygen around 85 kilometers, something like that. They send out a thermal emission, but that thermal emission also has what's called a Zeeman split to it.
Okay.
So when it looks down, it's supposed to be a line at a certain wavelength, but it is not. It has like 2 humps, and that's because of what's called a Zeeman split. Again, it's supposed to be one line at that particular wavelength, but in reality, it splits into 2 lines. And that's because there is a magnetic field where the emission is, but we can use that. We can literally look at how much is the distance between the split of this line. And that allows us to look at, basically calculate what the field is, magnetic field is at the altitude of emissions. That has been used on the sun for decades. We're the first ones to do it on Earth here. And by looking down again, we also do it much more precise as it's ever been done on Sun, frankly. We get the full set of information from this Zeeman split, so we can calculate what the vector magnetic field is at 85 kilometers.
Okay.
And for that, we can then calculate what the currents are in the ionosphere. So essentially, we get a bit of light, and we calculate what the magnetic field is by carefully measuring the light.
So it is like a light difference, and the light shifts a little bit. Like, are we thinking visible light here?
It's actually in microwaves. So
microwaves.
It's 118 gigahertz is where the split is. So
Gotcha.
we have the MEMS instrument, which is, Jesper, help me out. It's the microwave emission. I can't remember what the 2 M's are.
Yeah. So it's not a visible wavelength.
Right.
It's a very long wave compared to our visible wavelength. But again, it's supposed to be just one line.
Right.
Because of the field, it splits into 2, and we can measure that distance between the 2 peaks, and that is the magnetic field.
So the stronger it is, the more it like splits it out, the stronger the electric field, the more it splits it, or the less it's, I don't know.
The longer it splits out, the stronger is the magnetic field, essentially. So we can literally just measure that distance. Now, It's more complicated than that, because we also have polarization. Just like you have polarized glasses at the beach and so on. We have the information about the vertical and different polarizations, and then we can get the vector magnetic field. But essentially, think of it as 2 line splits, and we can measure the distance.
Okay, that makes sense. Go ahead, Lisa.
Just for perspective then, so this is the first time that it's ever been done from up above it, right? That's what makes it so special. How were we studying these things before? From the ground, or flying like rockets through it, or how are we actually getting that information?
Wonderful. So essentially, the Electrojet flew at an altitude of about 115 kilometers, 110 kilometers, something like that.
Okay.
Problem is, that's too high for balloons. We cannot get up there. Of course, it's too low for satellites. If you get down there, they burn up. You're done. So it's in a layer where we have very hard to get to it. And here's the more interesting thing. That layer is where all the mystery resides. The entire Earth-space coupling occurs in that thin layer that we cannot get to. So, of course, the interest has been there for decades. How do we get there? So you make measurements from ground, but now you're at a distance of 100 kilometers or so. So everything gets smeared out and so on, and the signal gets weak. Then we have tried, just like you said, tried to shoot rockets through it, but they go up through it, and then they come down through it. And it's hard to generalize from a single event of 2 points, essentially.
You need a lot of rockets.
Rockets are wonderful, but they have also limitations like anything else. Then we've tried from space, but then the satellites are maybe at 700 kilometers or 400, 500 or something. And that's also a long distance from these electrojets and this layer. So we have a hard time probing into it. But by looking down and seeing this layer of emissions very, very close to the electrojet, you can almost see the layer. And what we are essentially doing is we're taking images of the electrical currents. And that has never been done before. So that really is groundbreaking.
Gotcha.
Super cool, right? So.
Okay. Let me get some questions here that have come in, and I think this is sort of an introductory question for each of you. What was the greatest challenge on the mission, like from a science perspective, then from an engineering perspective? Did you have to solve anything new? I mean, you didn't just go down to the Electrojet imaging satellite store and buy a satellite, right? You had to design the sensors, design the systems, put it all together, and then get it into orbit, into the right place. Let's start with the science side. What's the most challenging thing that you had to solve from a science perspective?
I think for me, it's very simple, frankly. It's this completely new way of doing things. Again, we look down, we get a bit of emission from this layer at 85 kilometers, and voila, we're able to get the vector magnetic field. That is almost a little bit of black magic here. If you tell people, scientists will look at you and say, is that possible? So even though you know the principle, practically actually doing it is incredibly challenging. You need to measure this very precisely. So for me, the biggest concern was how do we convey to the reader and to anybody there that this is going to work? And how do we convince ourselves that it's going to work, for that matter? But now we know that it does work, and it's really a new way of doing everything in terms of magnetosphere, ionosphere physics. So that was the biggest challenge in my end. I don't know, Rob, how about you?
From the engineering side of things, one of the things that we do with EZIE is usually APL or JPL. We usually build the satellite and the instruments, and we put the whole package together. For EZIE, we're in a new world order where you actually go to a satellite provider. In our case, this was Blue Canyon Technology, and they will give you a satellite bus and tell you what your accommodations are. So they will tell you, this is how much power you have, this is how much heat you can generate, all the rest of it. And then you have to work within those requirements. So working with a commercial vendor, working within their list of parameters that you have to fulfill was probably the hardest thing.
Gotcha. So instead of doing everything from scratch, you had like, here's a satellite bus. When we say satellite bus, we mean like a satellite framework. It's got things like power and it's got the structure and those sorts of things, but then you put your special sensors and systems and communications and stuff on it. But that's what you mean by a satellite bus, correct?
Yes.
So sort of fitting into that pre-existing, here's the slots, here's the power that you have access to, I guess, right? You have to sort of make your mission fit into that versus, oh, we're just going to do it all from scratch and design a bespoke satellite like from scratch, right?
There was one point early on in the mission formulation where we weren't certain we could actually get it into a 6U form factor. And so we had to fight really, really hard to get everything down to size so that we actually fit within that form factor. Because if you go up by another size, then whole different set of requirements, whole different set of launch requirements, all sorts of trouble. So we were literally kind of shoehorning this thing into the box.
Gotcha.
There was one case where they couldn't get the lid back on the spacecraft, and they were like, oh, what do we do? And so
if you look at the early pictures of the spacecraft, it's looking down and the solar cells on top. But if you look at the later, it's tilted because we figured out that we couldn't get the look direction, so we have to tilt the spacecraft and drill a hole in the side of the spacecraft to get the look. So you play these little games, but I think this also makes it incredibly efficient, low cost and innovative. And in some sense, that's also a challenge, and it's something I think these days we need to meet. So we need to be.
The thing to remember is we are $65 million all in, and
right?
Includes the launch,
everything.
Gotcha. So it's interesting. You've designed the satellite. You get the satellite up into orbit. Well, I guess you have SpaceX get the satellite up into orbit. How does that sort of work? Like you have your 3 satellites. The picture we just saw, they were already packaged in the deployers, I guess, right? You deliver those whole deployers to SpaceX, and they sort of plug it into the little Christmas tree on top of the rocket, and they handle it from there.
That's right.
Do you deploy the satellite? Is everybody sitting there in a line and then everybody presses their button to deploy the satellite, or SpaceX does all that and says, all right, now you're all deployed, your satellite should phone home, and now it's up to you?
SpaceX handles that. So they'd handle the deployment, and they give you a list of rules about when you can actually then turn your spacecraft on so that you don't interfere with the other spacecraft. So you get deployed, you wait a little bit, then the spacecraft will then automatically deploy the solar panels, get power, turn itself on, and then go into a kind of beacon mode where it just broadcasts to say, I'm alive, I'm alive.
Right.
The other new thing that we're doing with this mission is BCT is a company, they provide the complete solution. So they have their own ground system and they have used commercial satellite disks to actually uplink and downlink the commands. So
Okay.
we work through BCT. So on the day of launch, this is the thing that people forget is we're in the conference room at 1 o'clock and the launch goes off and we're all cheering and going, great, it's wonderful. And then it's another 3 hours before we can actually make contact with our spacecraft. So I have to stay up and wait 3 hours before we got kind of the first call back from the satellite to say it was alive.
Yeah. So SpaceX is like, all right, the little light turned on that says that your satellite left and the switch opened or whatever. Yeah, I'm making that up. But
pretty much
takes it.
Actually.
This is pretty much it. Yeah, there's a little switch that opens, and now there's not a satellite pushing the switch down anymore or whatever. But you can't, or it can't be programmed to immediately turn on. The satellites need to spread out a little bit so they don't interfere with each other. So you're sitting there waiting, and they're like, yeah, okay, it's deployed. See you later. And it still hasn't phoned home yet. You have to wait for it to phone home, huh?
Yep. Yeah.
It's nerve-wracking.
It's nerve-wracking.
Right?
Fortunately, all three did phone home, and they all responded to commands.
Did you guys have, Jesper, you always keep referring to it as like your little babies, you're kicking them out of the nest and everything. Did you guys have names or like nicknames for each of the three that you referred to?
Names. Easy cheesy, easy something, and frankly, embarrassing, I forgot. So I guess they have names.
Might at one point been Huey, Louie, and Dewey.
Huey, Louie, and Dewey, nice.
But we rather boringly refer to them as spacecraft A, B, and C.
A, B, and C. At least it's not like 1B in Roman numeral 3 or something like that.
Still not
just
so
like a long serial number that's very like boring and dry.
Yeah. Okay, here's another. We ask this sometimes. We don't always get it because there's not always sets of satellites. Was one of the satellites different than the others? Like, did one give you a little trouble? Was it a little finicky, or were they just copies of each other and they just did the exact same thing? Or one, we actually had to tape a penny to one to make it turn on. Or I'm clearly making that up. Are they all just exactly the exact same thing, or was one of them a little bit finicky?
They all have their own little quirks, shall we say?
Okay.
So although they are actually all identical, just because of the way the fact they actually are handmade still. I mean, it's someone literally soldering boards together, putting them in cases and assembling the thing. They all have slightly different behaviors.
Okay.
So some of them we occasionally get soft reset where the instrument will shut down for an orbit, and we get more of those on one of the spacecraft than the other. And
Gotcha.
It's just luck of the draw.
It's like a little light is blinking in your control center. You're like, whatever, it's easy to, it's fine. It does that. It'll be back after an orbit. We have cameras like that. They're like, I know how that goes. I don't have any spacecraft, but every now and then it's like, it's whatever. It's the beach camera. It'll be back in 20 minutes. It's fine. It does that. It's funny how little idiosyncrasies, however you say that word, idiosyncrasies, line up when you build things like that.
That's exactly it. You learn how they behave, and they are individuals, and it's slightly nerdy, but you start to get to know, and they have a slightly different background of testing and so on, and so that's okay. But again, as long as they phone home, right, and send data home, they're doing that, then everybody is happy. So
they're doing their jobs.
As we saw of them with this movie, so it's there goes B, carambas. See you later, my friend. So take care.
I like how you say, see you later, my friend, like you're telling your friend goodbye. So here's a question. What's the power budget for each satellite? Is it like 1,000 watts, 100 watts? Like how much power are you working with the solar panels?
That is a very good question, which I do not have off the top of my head.
I think it's in the 50s of what?
Say that again, Jesper?
It's in the house?
I think orbiter average is 50s, in the 50s, 58 watts or something like that.
So probably less than 100 watts. So like a light bulb in your house, maybe a couple light bulbs with the LEDs and stuff like that. But the entire satellite, its instruments, its communications, everything like a couple light bulbs.
Yeah, pretty much. If you look at the spacecraft, you can see how small the solar panels are.
Yeah.
And we don't get that much power out of them. And that's all we got on board other than the battery. But yeah, again, back in the day, you used to have the big satellites and they were very, very power hungry. Now with everything being miniaturized and microelectronics, power budgets have gone down.
Yeah, I think a lot of people don't understand that. Like you're like, oh, it has a big generator on it or something, and it's like, no, it's way less power than your microwave in your kitchen uses, right? Like not even. You would probably love to have 1,000 watts, like a
We always
normal
want
microwave.
more power budget.
Yeah,
And
yeah.
we're
So
fortunate and easy in that we have just one instrument. Because I've been on other missions where there's been fights between instrument teams on the power budget,
Ah,
where they say, no, we do need a few more milliwatts here, and we can do some more science. And it's like, no, 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 we need it over here.
Yeah,
gotcha.
I think you're hitting on something important. I mean, everybody out there should realize that a scientific satellite is much like an IndyCar Formula One car. It's extremely optimized.
Ah,
It's to the limit of everything because you cannot just throw everything at it. If you start throwing everything at it, people start saying, hey, you know what? We could use that money or those resources for more science, just like Rob just said. So where you have a commercial satellite, typically it's as big as a school bus, right? These things are small, agile, incredibly efficient. They're built on much smaller budgets, much smaller budgets. Everything is squeezed out to the last, and we have to do that. So
yeah. That makes good sense. It's like efficiently using it. I mean, efficient use of space, efficient use of power budget, efficient use of the materials that you have. Like, did you have any exotic materials required, or is it all pretty much, oh, the satellite's made of aluminum? That's pretty straightforward, or whatever.
again, much of that comes down to cost, right? There used to be an old rule of thumb in science is the cost of a satellite is proportional to the weight. So you simply said it's so many pounds. Well, that's a cost. That was
Right.
an old rule of thumb because at the end of the day, it pretty much ended at that. Not in terms of the weight, but simply in terms of what you put into it. So it was pretty much proportional. So
Gotcha.
not sure it is like that anymore because just like EZIE here, we have incredibly efficient solutions to some of these instrumentation and the spacecraft. Even the notion of these CubeSats, I mean, it's all new in some sense. Even though it's been around, it really has hit the main only lately in terms of being actually used for real high-powered or high-profiled science
Right.
missions like EZIE. So
Yep. It is the thing, like originally CubeSats seemed to be demonstrators, right? Where it's like, oh, look what we can fit in this small package, or oh, we're going to power our satellite with a cell phone or something, right? But here, this is an example where it's a full science mission that you've done that you're fitting in the smaller form factor. You don't need a refrigerator-sized satellite or a dedicated launch just for your satellite. You can fit your science in the smaller package.
yeah, I think 100%. I mean, NSF really were making the path with CubeSats. They had a CubeSat initiative. Much of that over the years was really to develop the next generation students to get their hands on CubeSat. The entire concept of how do you communicate, how do you fly, how do you construct a satellite. And so once it was in space, the vast majority of the contribution or the gains had been done.
Right.
Now, if it actually did something in space, even better, but quite often it did not.
Right.
But this is different. EZIE is different. We have to actually a full-blown science mission. We have to produce science results. We have to close science questions. We have to finally end debates that's gone on for 50 or 60 years. And that's our job. So it's different.
That makes sense. Instead of just, oh, can we fit it into this size package, or can we get it into space and then have it phone home? You've done all that. That's all done, and you're delivering science. Like every time you go around the planet, or maybe not every time, but you're delivering science back from space times 3 satellites. That's your mission. Your mission isn't just to prove that you can get it there. You're delivering science on a regular basis, right?
Completely. NASA, again, once NASA pays you, you're paid to answer questions, not to fly. You have to close the science objectives that you state. That's what you're paid to do. So it's a different driver.
Alicia.
Let's talk about that. Yes, because you have had these up in space now for 3 months, and we want to know what you're finding. What are you hearing back?
Yes.
You know, what are you finding out now that you're studying these electrojets in ways that have never been done before?
So can we show you something that came down, Rob produced?
We have a very special
half an hour ago.
This is the
cannot
first
help
time,
myself.
the
Look
first
at
time
this.
anyone has ever seen this. This is
Wait,
breaking.
really?
Yes.
Let me just walk you through it. You see certainly our U.S. down below, and you see Greenland and so on in the picture. So you know how we oriented. This is a pass where we come from the day side and we fly over Greenland and we fly down towards Alaska and south. And then the 4 beams, what they did again, making the measurements of magnetic field. And they made it boom, boom. Every 2 seconds, the 4 beams made a measurement. And then we took those measurements and we derived what is the current system that is causing this magnetic field or producing that magnetic field. And that's what you're looking at. This is the first ever in the world.
Yeah.
I cannot be more proud here, so I'm happy. But this is the first ever snapshot from space, literally imaging how the electrojet is. What you're looking at is a whole lot of hair, so to speak. I don't know how people can see it. But those little vectors are essentially the currents. That points in the direction of the current, and you can see it's flowing towards Alaska, over Canada towards Alaska, so to speak. Underneath, there's a little bit of red there you can see. That's actually the magnetic field. So that's what we measure, and the vectors there is what we derive the electrical current that caused the magnetic field. So again, this is literally taking a snapshot of the electrojet, and the electrojet is that green, those strong vectors going towards Alaska there. So I mean, we cannot be prouder, right? So how cool is that?
Is there that was sourced like 50 minutes before we went live now? This is like cutting edge.
Wait, really?
You need to give Rob a little bit of a hand. But the entire team did this, of course. This has been in the works, but you're the first to see it. So
no kidding. Is the red and blue?
This is the first, never seen before, ever.
Yeah. Is that like the poles of a magnet? Red and blue, is that like a North Pole and South Pole sort of thing? Or is that...
Absolutely. That's exactly what it is. It's up and down, essentially pointing towards you, away from you, the red and blue. That's what it means. That's what we're using. So again, those are the measurements, right?
Yeah.
But this is the entire EZIE team making this possible. But again, Rob, he spit it out 15 minutes before we went live here.
Well, thank you, Rob.
Yeah, thank you, Rob. Amazing, man.
And so the green arrows, right? The red and blue is like the poles of the magnet. You said facing up and down, so like away from the planet or towards the planet. And then the green arrows, what is flowing there? Is that like a positive to negative thing, or is it like what is the vector that you're showing us?
It's literally an electrical current, just like the one you have in principle in the wall, driving your car. That's the electrical current. Here it's flowing westward, again towards Alaska. So that's what it is. And this is what we need. If we get these maps, we can again tell how is the structure. And then the next one comes by and we can see how do these green vectors, how does it change? What happened over those 5 minutes?
Right.
Now, you asked earlier, what if we waited a full orbit? That's 90 minutes. Unfortunately, the system has changed. It's a little bit like looking at the weather in your backyard and coming back next week.
Yep.
It's too slow. The system changes too fast. So it's got to be every few minutes we got to look at this current system.
Yeah, and
you're
that's
really studying the flow and the trends of things over time. Do you share this information with like NOAA or like the Science Foundation or like other agencies as well to help track like?
We share it with everybody. So NASA has an open science policy. So all of this data, the US public has paid for it. So we have to distribute it through our website to anybody who wants to come and look at it.
Gotcha.
This is free for everybody. Everybody out there can, in principle, go and download these once they become released in November. Right. In principle, you can go check them out, and you can do groundbreaking research at home.
So practically, you're looking at the currents. You have a couple bits of data, or not a couple of bits. You have a ton of data about the way the currents are forming, the way they're oriented. What can we do with that? Can we use that to predict how space weather will affect our communications on the ground? Like my satellite TV is not working now. Oh, it's space weather or whatever. What can we practically do with that information?
So this is an interesting thing. This is the entire space weather concept, right? So personally, I always got confused about that. It's two words, space and weather put together. Right. What does it actually mean? Now, the society we live in is more and more dependent upon the conditions that are in space. Even on ground, we see it. Directional drilling from oil companies, they use the magnetic field. And if you change the magnetic field, communication with spacecraft, used currents in power lines. We had a big power outage in Quebec in '89 that we burned a transformer and so on. But there are many, many examples of power outages caused by space weather. Right. So these are processes that take place, and they drive currents, and these currents affect our society. So knowing how the currents are behaving, how they're evolving, and that allows us to do predictions, nowcasting and forecasting. So it's a little bit like saying if we want to do space weather forecast on Earth, but we have no idea that a hurricane exists, then it's hard. We need to understand the hurricane to see how it's evolving and what is it going to do to our society. So it's the same with space weather. We are in our infancy, but we are learning. We are learning the processes and we are learning how these currents flow. So that's the purpose of EZIE.
Was there anything in particular that you were looking for when you first launched these? Like, was there a specific hypothesis you were trying to prove or disprove in studying these things, or were you just blankly just studying them just to see what they would
collect the data?
There's a picture 9, if you can pull up, that illustrates exactly what we are paid to do. So that shows essentially there are thousands of scientific papers that have tried to understand this. And what we realized in doing this mission is that all these thousands of papers had different ideas about how the currents would flow. But they kind of fell in 3 different groups, 3 different hypotheses here. The little black vectors here superposed onto the all over showed what the first hypothesis is, what the second one, and what the third is. Where they differ, as you see, is with the question mark. That's where they don't agree. So where they don't agree is, of course, where EZIE is flying. So you can see at the big polar plot there, that is where EZIE is collecting data. So the data you just saw before collected right in that question mark. And that allows us to say, hey, it doesn't look like hypothesis 1. It looks like hypothesis 2 or 3 or whatever.
Right.
So the pattern you just saw before, we're going to check that pattern and we're going to compare with these hypotheses and see, hey, does it agree with one of them?
Gotcha. So it's just an understanding of how, I say just, it's more complicated than just, but it's an understanding of how the magnetic fields make the solar wind and the electromagnetic radiation in space and all these different things, how they affect the Earth. I don't think a lot of people understand that. Like our power grid, the reason that the lights are on in your house right now and your refrigerator's on and your computer's working and all that sort of stuff, it's sensitive to solar weather. And when these big solar storms hit, it can induce currents in the power lines and the equipment, and all of the infrastructure has to be designed to handle that so that your entire power grid doesn't shut down when the wrong space weather hits it. You know, it's easy for us to understand, oh, a tornado hits a power line and now the power's out. Or a hurricane floods a coastal area and now this power isn't working or whatever. And not a lot of people understand that space weather, the electromagnetic, can have similar circumstances. It's not physically, well, I guess it could physically destroy things with induced currents. It's not knocking over a power pole or anything that you can really see, but it can still have serious effects on our power grid, right?
Right. And there is a very famous event from the 19th century called the Carrington event. You may have heard about this one.
Right.
And Reverend Carrington was a gentleman scientist, and he was out in his backyard sketching the sun, and he saw an interesting group of sunspots. And then a few days later, there was this massive solar storm that caused the aurora to be seen down in the Caribbean. And people could read the newspaper by the light of the aurora in London. And another interesting thing was that at the time, we didn't have power grids, but we did have telegraph lines. And the telegraph lines started to spark and the needles were jumping when no current was applied to the circuits. And that was the induced current from this solar storm. Now, if a Carrington event happened now, it would fry our entire power grid and fry every single satellite that we have in orbit. It was so massive. And we just don't know enough about the sun to know whether we are going to get a Carrington event tomorrow or in 100 years or never.
Yeah,
there's so much we don't understand, but yeah.
I may add something to that. Sorry.
You can really use this to study those trends then to see, oh gosh, it looks like something's getting bigger and swelling. We better watch out and watch out for falling starlings or something.
Falling starlings.
Yeah, the interesting thing is a small storm hit them and they lost a number of satellites that were in transit orbit. So as you know, and that was a tiny little event, right? But I think there's 2 different things with space weather. There's these spectacular events, and actually in 2012 we observed one from SOHO looking at the sun, and it was a massive injection, but it just missed Earth. And the idea was that might have been bigger than the Carrington event. It was so massive, and except it just missed Earth. We were just out of the shooting line, so to speak. And that was in modern day, so to speak. So I think it probably is a matter of time before something hits of great magnitude. So
Yep.
There's also the everyday thing when it comes to space weather. There are many things that are being GPS signal that are being disrupted or degraded. There's communication as you go over the pole with flights. There are a long list where, again, production and so on is disrupted, and there are different estimates of how many billions of years this cost, just the US, and it is very substantial. So there's the massive events, but there's also the everyday space weather, and this sort of indicates. This is from NASA. They had a space weather poster some years ago, a few years ago. I think there might be an updated one, but this is good enough. It basically shows a little list of the various effects on humanity. But there's also the satellites themselves, as you see, is sort of depicted here.
One thing that we should it's not all doom and gloom. Part of the reason we want to study space weather is so that we can understand this, and when we see these things happening on the sun, we can actually take precautions to defend against it.
Right.
So if we have enough warning, we see a huge CME coming towards us, the power grids can be configured in a way that they're safe. We can take action to save satellites and the rest of it. So that's what we really want to try and do, is to get us to a place where we can actually do that.
That's exactly the point. Oh, yeah, absolutely. Thank you, Rob. That's exactly. We need the understanding in order to make forecasting. You cannot make forecasting without having understanding of the system, and that's where EZIE fits in, right? So,
good deal. Alicia, how are we doing on questions? Do you have any questions? I can hop some from chat if you've got one to start with.
Yeah. Do we have more in chat right now, or should I keep going?
Yes, but if you have one, you go first, then I'll get some chat questions.
Well, I'm curious how you guys got involved in this sort of thing. I mean, obviously, there's some sort of love of space, I'm assuming, or maybe you have an electrical engineering background or something like that. How did you all fall into this line of your career? And I know you have two very different jobs too, so.
Want to go first, Rob?
Sure. So I am a self-confessed space nerd. So as a kid, I have bookcases full of books on space, because I'm old enough. We didn't have the internet back then. If you want to find something out, you read a book. So I have like the Cambridge Encyclopedia of Space. But growing up in the UK, there was no idea that you could go and work for NASA or you could work in the space business. We just didn't have that. We had ESA, but it was a different thing. And the UK was not very involved. Well, they are now, but at the time we were not heavily involved with ESA. So I grew up and went to college and took a degree in electrical and information sciences, and thought I was going to be a software engineer. And then I took a summer job just when I got out of college, working at the British Antarctic Survey, who have their headquarters in Cambridge. And it was a job to write software for these high-frequency auroral radars that were operating in Antarctica and the Arctic. And they were designed by APL. The network was called SuperDARN. And I ended up working as the software engineer on SuperDARN. And at the end of that year at the British Antarctic Survey, APL said, would you like to come over and work in the States for a year? Which I did. And then I stayed there. And then slowly over the years, I got moved into more space stuff. The first space mission that I was involved in was Van Allen probes. Did some work on Parker, and then I got the EZIE gig. So that's my background in it. It was all kind of serendipitous, almost.
I can
Software
see
engineering really is your background. That's cool.
Yeah.
I can see how the. Go ahead, Rob. Sorry. Go ahead.
One of the things that saying I never thought I would work in space. There are so many career choices that you can make that will end up with you working in space. It's not just the engineers, it's not just the scientists, it's all the other people that contribute.
Yeah. Thank you for saying that. We always like to emphasize that on every show. There's artists out there, there's communicators, there's software engineers like you, somebody studying computer programming who happens to love space might be programming a CubeSat someday like you. That's awesome.
I heard the joke slip out there. You got the EZIE gig. And it's like, oh yeah, I did all this stuff, and then I got the EZIE gig, and it's like, yeah, it's not really the EZIE gig. It's the complicated gig. You measure space weather, electrojet currents. Like, come on.
What about you?
I started as an engineer. I didn't like it much, so I went to the Bohr Institute in Copenhagen and studied physics, and I fit right in. And believe it or not, first time I saw the aurora was in '89, the event in Quebec. I saw it in Copenhagen. I cannot believe, but that is true. And I looked up and I was fascinated, and I remember it varying and waving and all that. And I thought, why does it change that fast? Why does it have those structures? And it baffled me. Why does it look the way it look? And I could not figure it out. So anyway, that was my path, and I went to NASA as a graduate student, went to APL, and then Rob and we ran into each other almost 20 years ago and have had projects. In terms of the EZIE mission, a scientist at APL came to my office and said he felt that he could do this Zeeman split. He's the PI for the mission, Dr. Sam Yee. And he said, I think I can make these measurements. Would that be useful? And it blew my mind. So I said, sit down.
Sit down.
And that was the start of the EZIE mission, so to speak. So it was a good combination of the retrieval understanding of being able to do it, and then the science in the other end, and then all the people, as Rob says, and let me emphasize that again, is the one thing that's humbling in life. It is a mission. You quickly realize that you are nothing but one piece of the machinery. Yep. And only if you all work together, managers, programmers, engineers, outreach people, only then can it become a success. So.
Yep. Even the most smartest person in the world only has a certain number of hours in the day, and working with other people and other folks with different specialties and stuff like that is really way more powerful than any one genius just operating alone. I think a lot of people don't understand that. We're too used to school projects where I have to do all the work and nobody else is doing the work. Missions like this don't work that way.
Well, I also want to give a shout out, if you don't mind, to JPL for building an incredible instrument, for BCT to build a wonderful spacecraft, for NASA to even believe in this craziness. We're going to look down, get a little bit of light coming out, and voila, we can solve 50-year-old, much debated hot topics, right? And they actually said, you know what? This might work.
So, You say look down. I think earlier you answered this a little bit, but let me explore this a little bit more. Why couldn't we take this sensor and put it on the ground looking up? Is it like the atmosphere just mushes up the readings or something like that, and it's better to be in the vacuum of space than down in the atmosphere?
Absolutely. There are instruments that are built on ground that look up, try to do the Zeeman. The problem is they take essentially 24 hours of integration to get a signal. The signal to noise is just so bad. You got to do it from space.
Okay.
But the ground magnetometers do help with putting the measurements from EZIE into context, because they are global. And that kind of almost segues into the EZIE Mag.
Yes, please. Tell us all about it, Rob. This is really cool.
So all NASA missions have an outreach component, which is a separately budgeted line item. And EZIE was struggling to come up with a voice and what they wanted to say in outreach. And Jesper and I, for years, because we work on ground magnetometers, have been tossing around the idea of, well, could we create a cheap ground-based mag that we could maybe distribute to schools?
Huh.
And we could never do it, never make it work, because the measurements we're looking at are measured in Teslas, and we're looking at nanotesla measurements, which is really, really tiny. The magnetometer in your phone is way too coarse to get down to measure that kind of signal.
Yeah.
So EZIE was thinking about this, so we revisited this idea, and there was a new generation of magneto. They are these coil-based microsensors. They're virtually micro machines that can do really, really sensitive magnetic field measurements down to the 7 to 10 nanotesla range. And they were also incredibly cheap. They were like $35. So on a whim one weekend, I ordered one of these off eBay and paired it together with a Raspberry Pi and got it functioning. And to my amazement, it actually worked. I could actually see the magnetic field changing. And
kidding.
It was sensible. I could actually go online to geographical survey, the professional magnetometers that the Americans produce, and then compare it with that. And it was in agreement. So I went back to Jesper and I said, hey, I think we can do this. And we took this as an idea to NASA, and they said, great. How much is it going to cost? And we kind of worked it out, and we worked out it would be about $200 a kit. And they said, great, make 1,000 of them and then distribute them. So that's what we did. So we spent the next 2 years refining it. We got an engineer in to help us design the circuit boards. We worked with the Raspberry Pi Foundation to get 1,000 Raspberry Pis. And that was in the height of when we had the shortage of materials, and you couldn't get them from anywhere.
Yeah.
And we literally called them up and they said, yeah, we can give you 1,000, no problem. And then we put together this kit. And so this is a kit that schools can order, and the kids can then put it together. It assembles like Lego. and it measures the magnetic field. It's got a little GPS receiver in there, so it knows where it is. It's got a temperature sensor and a little IMU sensor to tell it in which directions it's pointed.
Yeah.
And it works off a Raspberry Pi. So.
Does it upload the data back to you, or is it
No.
you download the data and submit it somewhere?
We did this very deliberately because so that what happens is the kids in school interact with this thing. So every day they will go and they will pull their day's worth of data and then upload it to APL so that they have some participation with it.
Gotcha.
And then they can actually look at the data themselves and they can work with it.
That is very cool. And the graph we were seeing there, that was sort of the proof that this small, let's say affordable, like it doesn't cost $100,000 for the kit. The data coming off of this kit that you sort of put together matched the, should I say, official observations or whatever the GIMA, right? I assume those are the official big measurements, right? And it was in basic agreement with those big measurements that I think are probably much more complicated instruments, huh?
Yep. Yeah.
Has that changed or influenced any of your goals for the broader project now, knowing that you're getting the same thing from up above and below now?
We're not quite getting the same thing, but we can now deploy many more of these ground-based mags. And it's actually changed the way that scientists are thinking about stuff. Before, it was, okay, we're going to make one very precise measurement using this custom-built instrument. And now we could have hundreds of cheap instruments that we can just deploy and basically throw away. But we can have hundreds of measurements versus one very precise measurement.
So knowing that this is working, I guess, now, are you guys considering any like further, more like mass production of doing this sort of citizen scientist like technique to learn other things, even beyond EZIE, I suppose? Or
yeah, I mean, we've got various groups are looking at putting different sensors into the box. So rather than having a magnetometer, you could do a thing called total electron content determination, which uses GPS. And there's other sensors that we can find to put into this box as well. So it's basically a system where you can add different sensors to it.
But there's a company that we're working with that is going to produce these so anybody can purchase them. And
I want one. I want to put one at Starbase. I'm at Starbase right now. I can put one over at in the middle of the beach at Starbase and see how the electric
everything is done very, very simple. You can pull it up on your phone and you can get the data off your iPad or your computer or whatever. You can see we was hit by a storm last year. I mean, we get hit all the time, and I pull it up on my phone because I have them in my backyard. I used to have like 8. And now I'm down to 3, and I think my patient wife, she says, "Are we going to take rent or something from all those Macs in the backyard?" But anyways, you cannot help yourself. You're like, "What's happening in space?" And you can look right in your backyard, and it's incredibly precise. Incredibly precise.
So we had a thing last year where one of our postdocs came up with a really cool idea, which is actually to deploy these magnetometers along the line of the total solar eclipse. And so he just put out a little text thing in the internal APL newsletter saying, if you're interested in deploying one of these, get in contact. And we had at least 50 people come and say, yeah, I would love to do this. And the little dots you're seeing on the map here are where each of these little EZIE mags were deployed along the line of totality.
Nice.
Oh, you guys, I think I read somewhere that you've deployed now like 700 of these now.
We're in the process of that. So we have go ahead.
Was that a cookie next to the kit in that last picture? Can we go back to
an
Oreo
cookie? Oreo for scale.
That's an Oreo for scale.
That's nice. That's great. Not a banana.
Let me add 2 notes to that. Everybody likes Oreo, so why not use that, right? So
the standard unit.
There's another thing. If you look at that background there, it's black, but we have them in gold and sparkles and you name it. And the reason is, again, that it's outreach, and it should be embracing. It should invite you in. It should not intimidate you.
Right.
So everything is done that way. It's like Lego pieces. You put them in. Everything is done simple. The operating system is done. Rob wrote all of that. I mean, it's done such that you can pull it up, as I said, on your phone and so on. And in terms of this experiment, it was kind of cool. There's an ancient old idea about a solar eclipse punches a hole in the ionosphere, essentially in the densities. It darkens. And when you have that, you should flow currents to the southern hemisphere, interhemispheric currents. And this allows us to do that because they're cheap. And if you saw the other picture from Iceland, there were people in Iceland, there's a group there, and they were interested in, they have a lot of lab activity, and you could probably see it in the background there. And they were like, can we use magnetometers to see the flows of lava underneath? And we can use.
Wow.
But they did not want to use the $100,000 magnetometer out on the lava fields. So they asked us, and we're like, here's 5. You can put them out there. You can see 2 of them here, and in that picture. So we are doing the analysis right now to see if we can see that. So people do cool stuff when this is available, right? And you'll be surprised how innovative and it's so cool what they come up with. So
yeah,
you're still rolling these out now, right?
Distribution is going to start at the end of the summer. So I think we're going to start sending them out to coincide with the new school year.
So how, if there's, let's say, like there's a teacher watching this right now, or just space nerd somewhere that wants to do this in their backyard, is it open for anyone to get one of these things? And how do people go about doing that?
Just go to the EZIE-Mag website, which is eziemag.jhupl.edu, and there should be a sign-up form there.
Even awesome. if you Google EZIE-Mag, it's going to pop up right away. EZIE Mag, it'll pop up. So,
yeah,
right at the top of the page
is schools or.
So we're open to.
There you go. And there's a button there for apply or something, how to apply or something. So
yeah, the top.
It's like, sorry, I'm not in the show anymore. I need to order my kit really quickly. Like y'all keep doing the show. I'm going to fill out this form to apply. I'm curious because we have camera equipment all around the massive Starship launches, right? And I'm super curious if there's anything that occurs in the plume of the Starship launch that would affect or be measurable by a magnetometer nearby. So I'm sitting here being like, I could put 3 of these. I could put one here and put one here and put one here. And then when that rocket takes off and makes this big dust plume and the dust is rubbing together, does that create anything that a magnetometer could pick up or something like that? I'm curious.
Put them at different distances and see what happens.
Yeah. See, that's the thing.
The other point that I should make is that we are actually open sourcing the kits.
Okay.
So we provide the circuit diagrams and the part list, and the software for the kit is open source as well. Yeah. But as Jesper mentioned, we have a commercial company who's going to, if you don't want to have to go to the hassle of buying all the parts and assembling it, we have a commercial company that we're working with who hopefully will make these kits available for sale. But again, part of the idea of EZIE-Mag was that it was a kit form, and you would get that experience of putting it together.
Yeah.
And also, as the software is open source, have at it, go and play with the software.
We'll make a video out of it. Like we'll assemble one and we'll make a video of assembling the EZIE-Mag, then deploy it next to the rocket launch and see what it collects. Like go back and get the information off the SD card. USB, it's probably like 5-volt power or something like that. I doubt it takes much power.
Oh, it's minimal. We're running off a Pi Zero.
Yep.
And you can run it off a battery for a few days.
Really? Okay, cool.
We generally ship them with these big 30-foot long USB power cables that you use for security cameras, and then plug it in the wall somewhere.
Yep, good deal. We have power at all of our sites. Go, Elysia.
Are there like parameters of where these work better? I live in the city, so like having a thing here in New York versus North Carolina or Starbase in Texas or something like that. Is that the idea that you just want them from everywhere, or is it maybe not as good in certain cities or things where there's a lot of electricity kind of everywhere around it too, and magnetic?
The further south you go, the less the effect of the magnetic field. It's still observable, but the field's stronger at northern latitudes because that's where the Earth's magnetic field is strongest.
Like funnels in, right?
Yeah. In terms of insulation, what we found the best way to do it is outside. If you put it inside a building, there's electrical wiring and the rest of it is going to confuse it. But if you put it outside, I have one in my backyard and in my front yard as well.
Nice.
Just in a cooler box. And that's running 24/7. And yeah.
I should see if I could set one up at the Intrepid. That'd be really cool.
At the Intrepid. Put it up on the mast or something like that.
Yeah, that'd be fun. No, that's really cool.
All right, so we're going to need to order 10 of your kits here so we can deploy them all over the place. And it really is awesome.
Cool is that the NSF team is literally all over the world, so we could hook you up.
Great. Yeah.
People everywhere, too, if that was available.
Is that you keeping it out of the elements, Rob?
I can't remember who. We had some interns last year who put
There was a
together
cooler.
the instructions and shot videos and stuff, and that's what that came from. But yeah, one of the things we discovered is it's heat sensitive. So in Maryland, where temperatures goes all over the place, put it in a cooler so the temperature is not moving as fast.
Maybe not
Gotcha.
the flight deck of the Intrepid during the summer.
I'm rethinking Starbase now, but Starbase is south, so not as strong electric fields, and it's really hot down here. So,
Here too.
so a question about the kits actually: are the schematics and software for the EMAG kit available so people can buy the parts and make one themselves, or is it sort of componentized? You can buy the kit that has a couple components and you assemble it yourself, or how does that work?
The majority of the kit was using just components that we ordered from SparkFun, I think it was.
Right.
There are some custom components. There's a custom circuit board that the Pi plugs into. We're making all of those drawings available so people can actually go and have those PCBs fabricated if they wanted.
There you go.
All the parts will be listed out, and the software will be made open. Well, it is open source already, but it will be distributed through GitHub so that people can get it from there.
No kidding. And it is you go to it and you like download the data off of it. You get it to it. It has a little Bluetooth or something like that, or some way you can connect to it. You can download the data. This was the nice thing about using a Raspberry Pi rather than an Arduino, because the Pi, it's got a full Wi-Fi chipset on that. So you actually connect by Wi-Fi. Okay.
And the way that you actually talk to the kit is it's running its own web server on the kit. And then you go to that web server, and then you can then download the data from there. You can see it operating in real time. Yeah, you can see on this page here that there's a page to download the data.
Yeah.
So it was designed so that you could interact with it.
That is too cool, because it's not, I'm going to say once again, it's not just collecting the science, but there's also the outreach, sort of the maker thing. Like, here's how you put this together, and you can put this together. Look, this goes here, this goes here.
So part of this goes back to when I was growing up as a kid in the UK, we did not have science fairs in schools. So when I came over here and my niece and nephew were going through school and they had science fairs, I was like, out of the way. I'm doing this for now. I'm doing the science fair.
Out of the way.
So I came with it with that kind of philosophy. Yeah, it's got to be an interactive thing that they can do. So yeah.
That's really cool. And I know Raspberry Pi is a language that a lot of kids are learning now, actually, in school and whatnot. So it seems like a really accessible, really wonderful opportunity for kids to tinker and to learn and create.
This is the thing, because as you said, with the Pi, they can get in there. The software that actually runs the kit is all written in Python. So they can go and extend that, and they can try different things with it. And they can try that in both software and with the hardware.
No kidding.
I think it should be mentioned that historically, worldwide, there's been about 600 Science Mag deployed in the history. And we are going to deploy 700 in this scoop, just to give you a sense of perspective.
I like it.
What we're doing, so.
You mean Science Mag, like science magnetometers to record
science
data?
Quality magnetometers, right? So
you'll double the number of deployed magnetometers making measurements with this project alone.
Oh, yeah.
That's cool. It really is. I mean, the advent of consumer electronics and miniaturization, and our cell phones are more powerful than the computers that went to the moon. You know, all these things you hear. But this is a real outcome from that. Like, here is now a consumer kit that you could have and you can put together, and it's not $100,000 for this, right? And then you can measure these really sensitive measurements in your backyard or whatever. It really is something that just did not exist 20, 30, 40, 50 years ago. It just wasn't a thing. We weren't carrying around little computers in our pockets, right? And now we can do that. Yeah.
And then ultimately all of the data, once these things get, sent out to schools and everything, you guys will incorporate that into the major mission database and learn more.
Yeah.
Remember?
Thank you for saying that. Let me just say this. I cannot believe you just asked that. So two things. One is that we actually asked and wrote a paper. We had a graduate student doing this. What if we fly overhead, but down below there was a magnetometer? So when we do deriving the electrical currents you saw earlier, what if there was a magnetometer below? Could that help? And actually the finding was, yes, it helps us. So if you do these magnetometers and we get them available and it is really run well, it actually helps us to do the solutions. So that's the science part. The other part is that as we're going back to space weather, we started out as space weather is inherently a global thing, and it's constantly varying, it's structured and so on. And it will require a massive amount of data to put into it. It's a little bit like weather stations. You need many weather stations to get a weather forecast. They measure for different kind of parameters like pressure and winds and so on. And we will need the same for doing space weather forecasting. We will need observations. So how do you get, for example, 50,000 magnetometers around the world? We're going to have to face that challenge and maybe be innovative and come up with these low-cost solutions that are really easy to use, easy to deploy, but are super low cost and still science quality. We need to think outside the box.
Or think in the tiny box that you'll put in your backyard, I guess, in a way.
Thank you, Alicia.
Correct.
I've got another chat question here. Let's go back to some of the science that you've gotten from this so far. I know that you sort of illustrated it with, hey, here are 3 different hypotheses on how this may work, how the currents actually flow, how they're oriented, and then, oh, the data doesn't match this hypothesis, it more closely aligns with this. Is there anything that you've discovered in the data that's surprising? Like, wow, wait, it does what? We didn't expect it to jump like that or curve like that or something. Have you seen anything like that?
Yes, but
not yet. We are still very early on. I mean, we are still going through the early stages of EZIE, again, the science investigation. So we're just getting the best out of the data, so to speak, and we are still doing the massaging. But I have no doubt that that's going to happen. Every time people get new measurements, and this is truly new measurements, a new way of doing everything, somebody's going to come up with something brilliant. And the data actually provides much more than what they're designed to do, which is the magnetic field. They also provide some sort of temperature measurement in the upper atmosphere, neutral winds, the winds at that upper atmosphere. And some of these measurements are sort of bonuses. And somebody, I have no doubt, is going to do something really, really cool. Somebody's going to have an idea that I never thought of. So, and do that. But it will take a little bit of time and let people be innovative and creative about it. So currently, I would say no, but just give us a little bit of time.
Well, what I would say is the thing that has surprised us is how well the instrument is performing.
Well, that's a good point.
The spectra that we're seeing are very, very clean. They're not noisy. Usually, there's a long period of, the signal's not as where you want it to be, and you have to calibrate it and all the rest of it. These are really clean signals. So we're absolutely 100% confident that we can get the measurements out that we need.
At the end of the day, the spacecrafts are behaving fantastically. The JPL instrument is unbelievably clean. So it's just a matter of time before we're going to get everything sorted out, and it'll be beautiful.
Yeah. I think, let me address this real quick. I think we may have sent too many people to your website because some people are saying that it's slow to load, but it's working fine for me here on my laptop. So if you're trying to go to the EZIE Mag website and get more information, it did load for me just fine. I wonder if we didn't just have too many people click on it at once. Not a bad problem to have, but I'll paste it.
You're going to have so many people sign up now. This is great.
I'll paste it in chat again.
And I'm going to get a phone call from our IT people on Monday.
They're like, what did you do? Where did you post our link? It wasn't ready to post yet. Well, I just posted it again. But that link right there, the EZIE Mag, spelled out, EZIE Mag, M-A-G, at jhuapl.edu. If you click on that I just put in the chat, that does come up for me. If it loads a little slow, well, too many of you clicked it at the same time. So just you get in line, form a nice orderly queue, and everybody click one at a time so the page will load for you.
We are grateful.
It's such a cool project. It really is such a cool project, and it fits in the little case, the little waterproof case, and everything. It's just such a cool. I think a lot of missions struggle to figure out how they can interact and how they can engage with people that way. And y'all have a really awesome. Hey, yeah, here's a magnetometer you can deploy at home in a little case. It's USB powered. There, just plug it in. It's fine.
Well, Jesper and I are always concerned about outreach and the next generation.
Yeah.
And we didn't want to have an outreach program where kids felt like it was an afterthought and that they were not participating in the mission. It was at the beginning, it was how can we get them to participate?
Yeah, I never want to knock outreach, but sometimes it's like, oh, here's the outreach. It's a page to color. right? And that's cool. There's a lot of places where that's great and an activity to do, and you still sparks the conversation, etc. This is a couple orders of magnitudes more engaging than a coloring book or something like that. Here's a comic we made, like all these different things that people try. This is real hands-on. Like when you do this, you are being a scientist. You are being an engineer. You're putting the circuit together. Go, Alicia. Sorry.
Stumbled on something really cool here, I think, because not only are you teaching the skills to put it together and make it, with your instruction kit and everything as well. They're learning electronics. They're learning how to build something cool. But then you can also have them, report back and check in on it and see how it's doing. And it's also helping the data project too, which is really at its core. You're having them do work for you too, which is great.
Yeah. Well, what we're also doing is we have, if you go to the website, to the gateway part of the website, they will upload their data from their stations, and we have a little map with little dots on it where all the stations are, and then you can plot other stations, compare your data with other sites around the country. And then, like I say, you pull the data off the kit yourself, you can do your own analysis of that data. So we're going to provide tools and hopefully some instructions on it. Well, how do you look at this magnetic field data?
Graph your own.
That also then, allows teachers to maybe build lesson plans out of that sort of thing, and teach them to use the scientific method and have their own little challenges in their classrooms and stuff. That's brilliant. What a wonderful idea.
We have an absolute amazing outreach team, and this is a new world for me, and I'm learning all the time. But I think the philosophy again with this EZIE again is that don't forget that the little intimidated girl in the corner could be more talented than everybody else in the class, right? And that means that everything here should be embracing and inviting, as I said earlier. Yep. So we have funny colors, everything, you can do it and so on. But in terms of everybody, if you have it in your backyard and you see it, as I said, I cannot help myself to see what's happening right in here and right now. I can literally see pressure pulses in the solar wind hit the magnetosphere, and I can see it in my backyard. I can see, boom, we just got hit. So in some sense, that magnetometer is so precise that what it does is actually it measures the magnetic field, but the magnetic field is produced by electrical currents flowing between space and Earth over hundreds of thousands of miles. And by seeing those little wiggles that you see in your backyard, you can literally see, as I said, not only that the magnetosphere got compressed by the solar wind, boom, you can also see how the currents change. And essentially, as I illustrated it to my little girl, I said, what they really are doing is that they are listening to how Earth and space is communicating. The way it's communicating is electrical currents. And this allows you to listen to that conversation. And at that point, my little girl, of course, asked, I get it. But what are they saying?
Well, you're going to have to plot the data.
That is the entire purpose of the EZIE mission, isn't it?
Yep.
What are they saying?
That's so cool. What a great way to put it, too. They're talking to each other, but what are they saying?
Yeah. Well, so Alicia, we're going to need to order a few of these kits. We'll record it. We'll make some videos. We're going to have to go up north. So we'll visit like Norway and Alaska and Canada. We have some places to go.
And that's the funny thing. You will see the magnetic field anywhere on the globe. It doesn't matter where you live.
I'm trying to get a vacation, though, like back up to Norway or something.
I still have never actually seen the Northern Lights. I can't, even when they were here in New York, I was like out of town or just like it was cloudy. Thing. I still have not. I am dying to. I've been to Iceland. I've been like a lot of places that have them. I've just never seen them.
I've seen the northern lights to the south of me because I was working on one of these Arctic radar stations, and the guy I was working with said, "Come outside." I said, "What?" He said, "Northern lights." So I looked north, and he says, "No, they're behind you." You're so far north. The aurora are actually south of that.
They were south of you. No kidding. Oh, geez. All right, Alicia, as always, we come to near the end of the time. I know we've got some other commitments y'all have here this afternoon. Any questions we missed? Did you have any hanging question that you wanted to ask here at the end of the show? We've got about 4 minutes before we have to let our guests go.
I mean, this has been incredibly informative. I think this is fascinating. I guess just the last question I would have is just, what does success look like for this mission? I know you have certain things that you said that you needed to try to prove one way or another, to launch it in the first place, but even larger than that, like in terms of outreach, like educationally or culturally, like what does success look like to you guys for the EZIE mission? Or have you already achieved it? Maybe even just getting it up there and getting some information now.
So can I say a few things, and then at the end maybe we can show the movie that that is really a very, very cool movie. I think it's called Movie 5 or something.
Movie 5, Jay.
But I think success for me, there's two different kinds here. There's the official success, which headquarters, we need to declare this mission, and that means answering the science objectives. We will do that. But there are also other things, the broader impact like we just saw. And that is getting people involved, getting people to realize that we live in an amazing world, and asking questions about that world is a good thing. Earth is constantly interacting with the surrounding space. And that's what this movie is partially showing. Here we see one EZIE and the other three passing over and we see our civilization below affected by all this. We live in a magnetic Earth here, so we have a massive magnetic field, and that's what these lines illustrate. This is, by the way, not illustrated. It is a full cutting-edge simulation of the entire system. So you see, this is not a simulation. It is a full simulation, not some animation.
It's not just graphics to be pretty. It's based on data.
Thanks for saying that. We saw the southern light, northern light. And here you see these contours that are coming. Those are the electrical currents that we've been kept talking about. They flow all over space. They flow at the magnetopause. They flow at what's called the cross-tail sheet there. And you see how all these field lines are constantly evolving, and that's associated with these currents. They're all the same side. And you see how this system, again, is evolving. If you have a magnetometer in your backyard, you can listen to all this. You can see all the little wiggles, and they will be sensitive to these currents that you see, all those contours, the beautiful contours here. But there's another thing here. If you look up magnetosphere on the Google, you'll see 2D plots. But the world is not 2D. And all the science EZIE does is in 3 dimension, and that's what this EZIE simulation is meant to be. Don't forget the 3rd dimension. That's where all the cool stuff lives, right? So, and a particular one to Slav American here, shout out to him, but the planetarium too. So Rob.
That looked alive. Like all the constant changing, flowing electrical currents and connections and stuff like that. It's living. It looks like it's living and breathing and constantly changing. It's not just a static, invisible thing.
That's actually
the world we live in. And that's what space weather is. It's affecting us all, right? So
yeah,
it's a very good point there, is that we're now creating these animations and these simulations to show people how dynamic it is. Because traditionally, you see a plot, a static plot, the aurora or a picture or whatever, but actually showing it in motion, showing people exactly how dynamic the system is really important.
Yeah, you see, you know what the magnet lines look like, and they're little lines that look like this, right? A little donut or an apple or whatever, and you always see them, and they're just static. It's just a drawing. And when you see it flowing and changing and stuff like that, and then with your mission and your satellites, you get the resolution, 3 satellites in a row, take a measurement, wait a couple minutes, take a measurement, wait a couple minutes, take a measurement, and you're getting that data to illustrate that ebb and flow and flux between, I guess flux would be a good term for it, between all the lines there. It really is cool to illustrate. Okay. We've come to the end of the show. I just want to keep talking, honestly. I want to talk more about the kits and stuff like that. But Jesper, I know you've got some commitments. Rob, you've taken time out of your Sunday here to spend time with us and tell us about not only the cool mission, the EZIE mission that is mapping the, I can't say the whole thing, the Zeeman currents, the Zeeman separations, the whole thing that's being mapped. And then the little kits, the EZIE mags that are available for folks to do some of this citizen science and gain an understanding. It really is just an amazing thing y'all have put together. Thank you so much for taking time out of your weekend to share it with us here. We really do appreciate it.
Thank you for having us.
Thank you.
All right.
Thank you.
Good deal. Alicia, do we have a thing about the next show we're going to do real quick?
Yeah, actually.
Let's do that.
So next month, our next show, we are going to be back on site again at the Intrepid Museum for our next Astro Live program. You can also, of course, tune in on the live stream as well. But we are going to be thrilled to have with us not 1, but 2 astronauts. So next month, we are going to be hosting 2 of the Polaris Dawn astronauts, Sarah Gillis and Anna Menon. You might recall that Polaris Dawn was a mission that, we've all been following, and we watched it launch and saw them do some really amazing, groundbreaking stuff. It was the first first commercial spacewalk, the highest orbit ever flown by humans, and the inaugural use of Starlink in space, all sorts of different things like that. And Gillis and Menon are amazing. They are both engineers. They were mission specialists on this, and they're going to be joining us on site at the Intrepid Museum in New York to talk about their experiences. So come join us on site if you can, or of course tune in as usual on all of the channels that we stream to via NSF, via Intrepid Museum or Kerbal Space Academy. And we're really excited about that. And also we are excited about another thing. At the end of this month, June 26th, we are opening a brand new exhibit at the Intrepid Museum. We invite you to dive into the fascinating world of underwater archaeology. So this actually is blending cutting edge technology and expert teams to uncover hidden things beneath the waves. So, you know, oftentimes if there's a plane that goes down or something like that, or maybe a rocket booster, let's say, that drops into the ocean, it's how they actually are able to find them and explore them and learn more about the past and also just what's down there and what caused things to go down too. So we've got this brand new, very immersive exhibit. It's 9,000 plus square feet, bilingual exhibition, co-produced with the Intrepid Museum and Flying Fish, who also produced the Apollo When We Went to the Moon exhibit that we had last summer. And it's located right behind me. It's actually going to be underneath the Space Shuttle Enterprise in our Space Shuttle Pavilion too. So be sure to come check that out. And once again, it opens in just a few days, June 26th, and it's going to be running through January, actually, so kind of 6-month unless we extend it. It's very immersive, as I mentioned, and really interesting about underwater archaeology. We've also got this coming Friday, our movie night, of course. We're tying in all of our summer movies as well to underwater archaeology. So we are showing Pirates of the Caribbean, Dead Man's Chest this Friday. They're searching for stuff underwater. Come on.
They are. I guess that makes sense. They're searching for stuff underwater.
And then July 25th, again, our astronomy night, when we've got our astronauts for that presentation. We also are going to be showing The Abyss because there's the alien tie-in. If you've ever seen the movie, you know, they're searching for the submarine that goes down and they find the alien spacecraft down there. That's not really too much of a spoiler. It's pretty cool. Really. And then we're showing one of my favorites, the cult classic Atlantis, the Disney Atlantis animated movie in August as well. So please, if you're in the New York City area, come by and check out our fun movie nights. And of course, come meet Anna Menon and Sarah Gillis from the Polaris Dawn program next month.
And in the meantime, if you're interested in learning more about the EZIE mission, the NASA EZIE mission, we put some of those links in chat. There's tons of information online. Remember, spell it out. It's EZIE. Lots to learn about the mission. Massive thanks. We need to let our scientists and our engineers here go.
Can go if you need to.
We need to. They have to go to another thing, and we're keeping them after time. But thank you all so much for taking time out of your weekend to share your awesome work and your awesome mission with us, and we will see you later.
And here we go. We have liftoff.
Propulsion continues to be normal.
R68 chamber pressure looks good.
Rolling up. Roger, roll, Atlantis.
Water towers fly! Yes! Tango down to nominal.
Flight downside FD off. Bring in FD off.
It's orange!
Orange 25. Oh my god!
Oh my god! Decollage!
What is it?
Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This methane will be igniting in the flare, correct?
Yikes. You good? We don't need any more of these.